My name is Rebecca Williams, and I will be presenting our research into GNNs for genre classification. In total, there were two main goals we wanted to accomplish. Starting out, we wanted to gain an understanding of GNNs, otherwise known as graph neural networks. This later evolved into an experiment to find out if the relationships between book entities can indicate book genres. Now, the thought process behind this was pretty simple. GNNs use graphical inputs. There are also many different pre-existing book graphing algorithms. This led us to the question, if a book's genre is based on story elements and structure, and book graphs model these concepts, can a GNN be used to classify books by genre? Now, before we detail our methodology and results, first some background. Graph neural networks are a special type of neural network that utilizes a graph input. Now, in these graphs, nodes and edges carry information. The graph neural networks are designed to handle different tasks in the graph domain. These node, edge, and graph level tasks are functionally different, largely due to how data is aggregated or pooled within the graph. Now, specifically for our research, we utilized a model called Graph Attention Network, otherwise known as GAT. Now, this model was introduced in a 2018 paper, and its main feature is the graph attention layer. Now, this layer calculates the importance of one node's feature to another, sans graph structure, though it is artificially limited to the area around a given node. Specifically, we used the improved GAT v2, which showed better accuracy by using dynamic node rankings. Now, moving on to methodology, we'll start to discuss some of the finer details. Books were sourced using Project Gutenberg, a website offering copyright-free books for download. In total, 132 books were downloaded across 12 genres. Genres are identified using Goodreads user rankings, specifically using the top user-purported genre for each book. Now, graph generation relied on multiple algorithms, including pre-existing book graph algorithms, pruning algorithm, and PyTorch conversion algorithm. When it came to the book graph generation, we took two distinct approaches: a systematic grammatical approach and a named entity approach. The named entity approach utilized code from NLTK, otherwise known as the Natural Language Toolkit, and Lilian Tan's semi-rel to rel dict. This approach recognizes and extracts named entities, with relationships being between named entities in the same sentence. In contrast, the grammatical approach utilizes Nagesh Singh Chauhan's 2021 knowledge graph creation algorithm. Now, this identifies entities and relationships using sentence structure. In both cases, entities became the nodes of the graph, and the relationship between entities became the connected edges. In addition to the pre-existing algorithms, a pruning algorithm was designed to increase the relevance of data while decreasing the size of data. This simple method allowed us to eliminate entities that didn't meet a relationship threshold. In this case, the threshold value was calculated using the average node degree. Entities with a number of relationships less than average were culled. The logic being that, much like in book summaries, the important principal entities will have more appearances in text and thus a larger number of relations. Let's look at a comparison of different graphs generated for the same book. On the top left, we see a graph generated using the knowledge graph algorithm and the full book text. As you can see, quite a large volume of nodes and edges are generated. Looking to the right, we see a graph generated using 50% of the text and the same knowledge graph algorithm. Using the same algorithm on the full text proved unusable due to the large scale. Taking the middle 50% was one method we looked to scale down the size of the graph. Now, scanning down, you can see a graph generated from the combined efforts of the pruning algorithm and the knowledge graph algorithm. By pruning, we were able to eliminate minor entities, allowing for the use of the full book text. Finally, on the bottom left, we see the graph generated from the named entities algorithm. As you can see, its reliance on named entities makes it much more sparse. So I'm just going to cut in here and give a more in-depth look at some of the numbers. So when it comes to graph generation, in front of you, you should be able to see a couple graphs and a table. When it says number of nodes, number of edges, that's relating to the total number of nodes and total number of edges in the entire graph set. So calculating across all 132 books, across all 132 graphs, the total number of nodes and the total number of edges. So if we look at it, we can see when it comes to the graph gen algorithms that of course the full text knowledge graph algorithm produces the most nodes and edges, and that corresponds to what we saw when we looked at the original pictures that I just showed you. Now, if we look again, we see that kind of going down, we have the middle 50% knowledge graph. So that's middle 50% of the text using the same knowledge graph algorithm. And that seemingly has almost cut the number of nodes and edges in half when compared to the full text knowledge graph. Now we take a next step lower, we'll see the named entity. Now if you look at the named entity algorithm, you will see that it is marginally smaller compared to the prune knowledge graph algorithm. And I think again the pictures show that with the sparseness of it, due to the fact that it is looking for specific named entities as opposed to working just on sentence structure alone. Now, what I find the most interesting, and you may have spotted this, you will notice that when it comes to the number of edges, if you look at the number of edges picture, you'll see that the prune knowledge graph actually has a vastly greater number of edges compared to named entity, as opposed when you look at the number of nodes where they are close. Albeit, if you look at the actual numbers, you'll see that the prune knowledge graph has 567 nodes in total, and that the named entity algorithm has 692 nodes. So there is a difference. But when you scroll over, when you look to the right, in the right column, you'll see that compared to the 8,046 edges in the named entity algorithm graphs, the prune knowledge graph dataset has 100,000. So we're sitting out there at 142,121. That's 142,121. So it's a great difference. And that's largely due to the algorithm itself and the methodology of culling entities with the number of relations less than average. So because of that, we're left with a lot more. We're left with, one, being able to use the full text, and two, the grammatical approach allowing us to have more entities in total. So if you think, we start here at the full text graph column, and then once we put the pruning algorithm on it, though it greatly decreases, you would still expect, based upon the code itself, that it would carry a greater number of edges, meaning a greater number of relations, and a greater number of nodes. Now, the code itself can be found in the full report. After the graphs were generated using Network X, the Network X graphs were then converted to PyTorch data objects. Now, these data objects allowed us to access the PyTorch geometric GAT model. The conversion process was fairly simple. First, the text data was converted to numeric data. Entities and genres were assigned unique numerical labels. Relationships were converted into sentiment analysis scores using NLTK's VADER, VADER. Each relationship was given a negative, neutral, positive, and compound sentiment score. Finally, all graph values were converted based on PyTorch documentation into tensors, from which data objects were constructed. Now, on to the experiment. In total, 3 data sets were tested across 4 different GAT configurations, each configuration sharing the same structure and parameters outside of a differing number of epochs. K-fold validation was was implemented using sklearn, and it was used to calculate the accuracy of the model. Fold loss and accuracy were measured, recorded, and visualized. Here we have an overview of the findings. A more detailed breakdown can be found in the full report. As you can see, at 10, 15, and 20 epochs, the most accurate dataset utilized the novel pruning algorithm, with configuration 4 having the highest average mean accuracy across all folds and datasets, and the highest fold max accuracy when compared to across all other configurations. Okay, I'm just going to jump in here and give a more detailed look at the numbers. So, here we have all the recorded data from the testing. Now, if you look at the first column, that's the model configuration column, model config, and it lists not only each config, but also parameters of each configuration. Now, you'll look closely and you'll see that they all have the same number of layers. The layers across the different configurations are the same in terms of size and dimension. So layer 1 in configuration 1 is the same size and dimension as layer 1 in configuration 2, and so on. The learning rate is also the same, as well as the batch size. The only difference is the number of epochs. So as we look here, we have these separated into folds. Now, as aforementioned, we use k-fold validation to gain our accuracy. So essentially, 10 folds, over 10 folds, you have per each fold the number of epochs. So for instance, for configuration 1, it's going to run 10 epochs in fold 1, 10 epochs in fold 2, 10 epochs in fold 3, so on and so forth. In each fold, the training set and the testing set are different. So each fold is almost as if you are running the test over again, if that makes sense. So essentially over 10 rounds of testing, you can call it, 10 folds. And specifically, I'll use configuration 1 as an example. So that's 10 epochs. So each round of testing, 10 epochs goes through. After that, you get this test accuracy value. So all these values are presented after the 10 epochs, what the accuracy value is. Of course, these are in percentages. So we could just go down the list. Now, there's a lot of numbers. It's going to make more sense when I get towards the end. But as you can see, we'll just keep going down. So it's fold 1, fold 2, fold 3, fold 4. All 10 folds are here. Loss values and accuracy values calculated. Now, what's interesting, if I can just pull all the way down at the end, I've color-coded this. So in the red rows represent the data, the tests using the prune data set. The green rows represent the test using the middle 50% knowledge graph data set, and the blue rows represent the named entity data set, as given by this key here. So we look, and the good thing about Google Sheets, and same thing with Excel, a lot of this work is done for me. So after pulling in all the test accuracy values, I can run a simple formula and get the max accuracy, min accuracy, and mode, which represent the first 3 columns. Now, because of how mode works, if there is multiple, if it's multimodal, we have overflow columns to kind of support that. So you can see here clearly all the max accuracy, min accuracy, and then the mode and overflow if necessary. And we're going to jump over, we also have a median, the average accuracy, a standard deviation, and IQR. Now, when selecting these benchmarks, I really wanted to make sure that the metrics gave us not only an idea of what the accuracy is, but also in the spread of accuracy. So we're testing a bunch of times, using a bunch of different test sets, a bunch of different training sets, which gives us a really good general idea of what the overall accuracy is. But what does that mean, really, and how can we understand that? So when we get something like median or mode and the average and standard deviation, all that helps me understand the spread. And I think that's very reminiscent, especially when you're looking at the IQR, Q1, Q3 in this candlestick plot, which functionally is very similar to a box plot. So you can see at these tiny little lines, those stretch from the min and max, and then the top of the first flat bar and the bottom, and the bottom of the box, so top of the box, bottom of the box, that's going to give you your Q1 and Q3 values. So you can really see where the majority of the data is sitting in regards to what we've collected. Now, I go into much more detail about this in the report, but just from visuals, you can clearly see that some configurations definitely have wider spreads than others. I can see by the varying heights or widths, I guess, depending on how you look at it, of the boxes. You can also see that some, for instance, in this, for the middle 50 knowledge graph data set, raster configuration 2, you see it also, this sits below the max, well below the max. In fact, the min is so close to the Q1 that you can barely see it in the graph. Now, that same kind of situation, same thing with this one for the named entities. And then here's an example where it kind of sits closer to the max when using a prune graph data set. In fact, if you look at a lot of these prune graph data sets, you'll see that when you look at the accuracy, it tends to sit closer to the max, if not in the middle. So that's the data. Back to the presentation. From our findings, we were able to determine that book entities and relationships can indicate book genres, and that changing the graph size affects model performance. Now, this can be seen by how smaller graphs seem to perform better across larger epochs, particularly if you were to go back, you could see that the prune graph data set performed better than the larger middle 50% book text knowledge graph data set, only being beaten out at 5 epochs. So at 5 epochs, the middle 50% performs better. All right. That concludes our presentation.